Hey everyone, and welcome to This Explainer. Today we're unpacking Lecture 14 by Skip Uni to really master the absolute foundation of programming logic, which is the C++ mathematical toolkit. We're going to uncover exactly how a compiler actually looks at and evaluates math under the hood. So if you've ever felt a little intimidated by what exactly is going on in system memory during a calculation, you are absolutely in the right place. Let's just dive right in. So let's kick things off with a seemingly super basic math question. What does 10 divided by 3 equal in C++? Now, if you're relying on your intuitive algebra expectations here, you're probably picturing a decimal right now, right? Something like 3.33. But in the programming world, your mathematical intuition is about to completely clash with the compiler's reality. The answer is literally just 3. No way, right? This is the ultimate gotcha moment for anyone starting out in C++. When the system sees two integers being divided, it performs what we call integer division. It strictly outputs an integer result and entirely ignores the decimal. It doesn't round up, it doesn't round down, it just brutally chops the decimal off. All right, moving on to Section 1, the C++ Math Toolkit. We can basically split all these mathematical symbols you use every day into two very simple families. On the left, we've got binary operators. Binary literally just means two, so these operators need exactly two operands, or values, to actually work. Think about it. You can't just have a plus sign hanging out by itself in your code. You need an A and a B. This includes your standard addition, subtraction, multiplication, division, and the modulus operator. Then on the right side, we have unary operators. Unary means 1. These are incredibly powerful specifically because they only need a single operand to function, like slapping a plus plus onto a single variable. Let's jump into Section 2, the integer division trap. So how do we actually solve that weird division anomaly we saw a minute ago? Well, enter the hero of our story, implicit type conversion. You see, a compiler follows a very strict hierarchy of data types. A floating point number, which is just a number with a decimal, is considered a higher data type than a standard whole number integer. Whenever you mix these two types together in a single calculation, the C++ compiler steps in and automatically promotes the lower data type to match the higher one. And here is exactly how we fix our trap. With standard integer division, as we know, 10 divided by 3 equals 3. But by simply adding a 0.0 to that 10, changing it to 10.0, we've now introduced a decimal into the equation. The compiler sees that float, triggers an implicit type conversion, and automatically promotes the final output to a highly accurate 3.33. It's a tiny syntax change, but it has a massive impact on your program's accuracy. All right, Section 3, mastering the modulus operator. Now, you probably saw the percent sign earlier in our toolkit. In C++, this is definitely not a percentage calculator. It's called the modulus operator. Unlike standard division, which is always trying to find the quotient, the modulus operator is exclusively looking for what is left over, the remainder. For example, 10 modulus 3. Well, 3 goes into 10 exactly 3 times, which gets us to 9, and that leaves a remainder of 1. So 10 modulus 3 simply equals 1. Now, you might be sitting there wondering, why on earth do I care about remainders? Well, this actually leads to one of the most common practical coding use cases you'll ever encounter, checking if a number is even or odd. If you take literally any number and modulus it by 2, the system does the math instantly. If the remainder is 0, boom, you definitively know the number is even. If the remainder is 1, the number is definitely odd. Developers use this exact trick all the time to filter data, create alternating visual patterns, and control their logic flows. Which brings us to our final stretch, Section 4, pre versus post increment. Okay, this concept stumps beginners constantly, and it shows up in pretty much every single technical interview. Let's set up a quick visual memory trace. We're starting with a base variable, an integer named a that currently holds the value of 10. We have two contenders here that look almost identical, but they behave completely differently in system memory. First, we have the pre-increment, where the plus plus comes before the a. I like to think of this one as proactive. Second, we have the post-increment, where the plus plus comes after the a. As Skip Uni describes in the lecture, this one acts a little, lazy. Let's actually trace the exact values step by step for the proactive pre-increment. Our equation is x equals plus plus a. The strict rule of the pre-increment is first increment, then assign. Because the plus signs come first, the system prioritizes the math. So step 1, it immediately jumps in and increments the value of a from 10 to 11. Step 2, it takes that brand new value of 11 and assigns it to x. In the end, both x and a walk away from this equation holding the exact same value of 11. Now, contrast this with the lazy behavior of the post increment. Our equation here is x equals a plus plus. The rule for post increment is first assign, then increment. Because the a comes before the plus signs this time, the system prioritizes the assignment. Step 1, it grabs the original unchanged value of a, which remember is 10, and drops it right into x. Step 2, only after that assignment is completely finished does the lazy system finally get around to incrementing a up to 11. Just look at the final results side by side here. With the proactive pre-increment, both x and a walk away equaling 11. But with the lazy post-increment, x is stuck holding the old value of 10, while a moves on to 11. These are just tiny, tiny shifts in syntax, literally just moving the plus signs from the front to the back, but they yield entirely different results in your system's memory. If you can visually trace this process in your head, you are already thinking exactly like a compiler.
So look at that. We've mastered our binary and unary tools. We've totally conquered integer division, we've harnessed the power of the modulus remainder, and we can now perfectly trace pre- and post-increments. But I want to leave you with a bit of a provocative question to chew on. What happens when we throw all of these into one massive complex equation? Like, if you have a post-increment, a multiplication, and a subtraction, all fighting for the compiler's attention at the exact same time, who wins? Well, figuring that out requires diving into the strict rules of operator precedence and associativity, and that is exactly what we'll be unpacking in our next breakdown. Thank you so much for joining me on this explainer. Keep practicing those memory traces, and I will see you next time.